There you go.
Hi everyone, thanks for joining us for Rounds. I would like to introduce Andrew Mente. Andrew has got his doctoral degree from the University of Toronto and his postdoctoral degree at McMaster in cardiovascular epidemiology. He's associate professor in the Department of Clinical Epidemiology and Biostatistics here at McMaster and a researcher at the Population Health Research Institute. And his main interest is in essential minerals, also sodium, and the association relation with hypertension and cardiovascular disease. And Andrew will tell you some more about that. Here you go.
Yeah. Thanks very much, Robbie. Hi, everyone. Thank you very much for inviting me to give a talk today. So the focus of my talk today will be on sodium, blood pressure, cardiovascular events, and mortality, and focusing mainly on the results from the PURE study, which we published in the past year. Now, cardiovascular researchers and public policy advocates have long labeled dietary sodium as the holy grail nutrient for reducing blood pressure and subsequent cardiovascular disease. And this has been a main focus of health research and public health policy since about the late 1960s, and in recent years has pretty much risen to a fever pitch. But is sodium reduction of the population supported by scientific evidence, or is it in large part conjecture? This will be the main focus of today's talk and discussion. Now, first, a historical overview. Salt has played an important role in human history. It's a pivotal ingredient. It has been a pivotal ingredient in the transition from hunter and gatherers to settled communities, and it acts as a way to preserve food during the winter months, and also in the raising of livestock and other roles as well. And it was an early trading commodity. In fact, the word salary is derived from the Latin word salarium, which was, so money was paid to Roman soldiers to buy salt. And since the early 1960s approximately, there's been research focused on understanding the role of salt in blood pressure and other health effects. And in the early 1960s, Dahl, in his work on rats, examined the effects of salt loading on rats, and he found that rats that were fed extremely large amounts of salt developed chronic hypertension. Now, it was only the rats that were bred to be susceptible to blood pressure responses to sodium that showed an exaggerated response to sodium, but the resistant rats did not. In 1970, the National Academy of Science Committee concluded that the evidence incriminating salt as causing hypertension was inconclusive. But nevertheless, the food industry found an opportunity to come up with low-sodium products, and they saw that there would be a market for that. And indeed, those products were introduced throughout the 1970s and were largely popular with consumers. And in the 70s and early 80s, despite an absence of published studies, U.S. federal agencies embraced salt reduction. So the claim that excess salt intake is harmful gradually became prevailing wisdom in the years that followed, despite the strong scientific evidence to support large-scale sodium reduction in populations. So the current dietary guidelines on sodium, most guidelines like the WHO and the American Heart Association recommend that populations consume anywhere between less than 2 grams per day to less than 2.4 grams per day, depending on the specific guidelines. And for high-risk populations to consume less than 1.5 grams per day. And that's a very low amount of salt. But are these recommendations based on good science, or are they an overzealous extrapolation of limited data? First, just to give you some information on definitions and the conversion of sodium to tablespoons of, or teaspoons of table salt. So less than 1.5 grams per day of sodium is equivalent to about 0.7 teaspoons of table salt, which is considered a very low amount of sodium. What's recommended for very high-risk populations. A low amount is about less than 2.3 grams per day, which is the equivalent of less than 1 teaspoon of table salt. Moderate is 2.3 to 4.6 grams of sodium, or 1 to 2 grams of table salt. And greater than 4.6 grams is considered a higher amount of sodium, equivalent to greater than 2 teaspoons of salt. So just be aware of the conversions. Most of the research focuses on reporting sodium. Now, the goal of population-wide strategies to reduce sodium are to get the general population, shown here in purple. So you see this is the distribution of sodium intake in the general population, like in a Western country like Canada, in the United States, with an average intake of 3.5 to 4 grams per day. To get that population shifted down to an interim goal of about 2.3 grams per day, and eventually in the long term to get the population down to an average of 1.5 grams per day. So these are large reductions in sodium for the entire population that have been the goal of public health policy. But is this 35 to 65% reduction in sodium consumption in millions of people necessary, safe, and feasible? So these are the questions we'll be focusing on. So the crux of the argument is that the blood pressure lowering effect of a reduction in sodium to low intake levels will reduce cardiovascular disease. Is this supported by the evidence? Well, first we'll look at the relationship between sodium and blood pressure, focusing first on the observational studies. The largest study that has been conducted up until recently has been the INTERSALT study, published in the British Medical Journal in 1988. And INTERSALT was a global study of about 10,000 people. And the investigators found a weak relationship between sodium and blood pressure, about a 0.9 millimeter mercury increase in systolic pressure per gram increase in sodium. And this is even after adjusting for random error. Now, in the Scottish Heart Study, which was published in the same issue of the British Medical Journal as the INTERSALT study, found no relationship between sodium and blood pressure in an equally well-conducted study. But in the years that followed, it was the INTERSALT study that was selectively emphasized by the scientific community, but the Scottish Heart Study was all but ignored. Sorry, which one? My understanding is that even in sensitivity analysis, where they excluded people with taking blood pressure medication, that there was still no relationship in the Scottish Heart Study. In the INTERSALT study, in various analyses that they did, the relationship was weak, no matter how you look at that data. So the Scottish Heart Study, it was a very well-conducted study. Over 7,000 people found no relationship. Now, it may be that, I don't want to get too much into the detail, but it may be that the fact that the range of sodium was pretty narrow, so you're not likely to see as a profound effect if you have a very narrow range of intake, whereas INTERSALT had a much broader distribution of sodium intake, so you're more likely to detect signals when there's a broader range of exposure. That's one possible explanation. Oh, yes? Yes. Exactly. Yeah. Yeah. In the INTERSALT study, they didn't adjust for population heterogeneity. They just took the communities and looked at the relationship. The primary focus was on the group level analysis, looking at the 52 sites. So it was more like an ecological analysis that they did, rather than at the individual level. And in that primary hypothesis, it was a weak relationship. And when you take out the hunter and gatherer communities, there were 4 primitive societies that were in the INTERSALT study. When you take them out, there was no relationship at all between sodium and blood pressure. So the slope was largely driven by the outlier hunter and gatherer communities in the analysis. But INTERSALT, as some of you might know, was a very, very controversial study and still remains controversial to this day. And how you interpret the data, it's interpreted entirely differently by different people. And then in 2001, the DASH sodium trial was published in the New England Journal of Medicine. Now, the DASH sodium trial has been the primary basis for current recommendations on sodium by the American Heart Association and the U.S. National Dietary Guidelines. The DASH trial is a proof of concept study as to whether changes in multiple aspects of the diet, including sodium reduction, would lower blood pressure under controlled situations, in that all of the food was provided to participants and their spouses during a short 5-week period. So the fact that it was a feeding study minimizes problems with adherence. So this is a very good study, a very well conducted study. But it was not designed to assess if sodium reduction also reduces cardiovascular disease and mortality in free-living populations. So just to show you some of the results from the DASH sodium trial, this is in Caucasian non-hypertensive individuals. You can see that, okay, on the x-axis we have the sodium level, high, intermediate, and low, and the y-axis is systolic blood pressure. You had the DASH diet and the control diet groups. The DASH diet group received a good all-around healthy diet, high in fruits and vegetables, high in potassium. The control diet received a very crummy diet that was low in potassium and lots of hamburgers and junk food. And you could see the potassium intake in the control diet was very low. It was 1.6 grams per day compared to the U.S. average, which is 2.6. So this was not a typical North American diet. This was a very, very bad diet. And now when people were consuming the control diet, you could see that sodium reduction resulted in a large, substantial drop in systolic blood pressure. But when people were consuming the DASH diet, you could see that there was very little and a non-significant effect on systolic blood pressure. And in looking at younger individuals without hypertension, you could see that when they consumed the low potassium control diet, you could see that sodium reduction resulted in a large, substantial drop in systolic blood pressure. But when they consumed the healthy diet, the DASH diet, you could see that there was virtually no change in systolic pressure. So the take-home message here is that the effect of sodium on blood pressure is largely context-driven, and that if you're eating an all-around healthy diet, the effect of sodium on blood pressure becomes smaller and smaller. Then in 2011, Grotto conducted a Cochrane review of the randomized controlled trials of sodium reduction and blood pressure. And as they're shown here in the forest plot, you can see that there's a great amount of heterogeneity in the effects of sodium reduction on blood pressure. Some trials showed a reduction in sodium, a large number showed no effect on sodium, and a few showed an increase in sodium. So there's a great deal of heterogeneity across studies. Now, of all these studies, it's the DASH trial that has been the primary basis of current recommendations. So which brings us up to the present in the PURE study, which we published 2 papers. We published in the New England Journal of Medicine this past year in the August 14th issue. In the first paper, we looked at the association of urinary sodium and potassium excretion with blood pressure. Now, I'll tell you a little bit about the PURE study first. Now, the PURE study is a large global study of over 100,000 people around the world. We had over 102,000 participants that collected urine measures, and I'll tell you more about that. And people were aged between 35 to 70 years from 667 communities in 18 countries around the world. So you can see here in this global map the countries and communities that were part of the PURE study. So it's a large study, and it's a global study of low, middle, and high-income countries around the world. And it's a prospective cohort study. So this is a very unique study, and really nothing like PURE has ever been conducted. Sodium intake was estimated from a morning fasting urine that was exclusively validated in 11 countries. So I'll tell you more about that in a moment. And standardized blood pressure measures were taken using an automated device. And then regression analyses were conducted to assess the association of sodium with blood pressure overall and in key population subgroups. And we adjusted for potential confounding variables. Now, I'll tell you a bit about the measurement of sodium and potassium intake. Now, 24-hour urine is the reference method for measuring sodium and potassium intake, but unfortunately is not feasible in large-scale studies, and under-collection of urine specimens is a problem. So you think of the PURE study, which has a large number of people from low and middle-income countries. A lot of these individuals are, manual workers or field workers. So it's not feasible to ask them to collect a urine jug for 24 hours and to collect all of the urine specimens during a 24-hour period. So in short, 24-hour urine collections are just not feasible or practical for large-scale population-based studies. So what we need is more new innovative approaches to measure sodium in large population studies. Now, a fasting morning urine has been used to estimate 24-hour excretion using a mathematical formula. It has been used previously first by CAUCASIAN in 1993. So we developed and validated a widely practical method to estimate 24-hour sodium and potassium in multiple countries. A fasting morning urine was obtained in over 1,000 participants in the PURE study. Sodium and potassium excretion were estimated from the morning fasting urine and applying the Kawasaki formula to estimate excretion. And estimated excretion was validated versus actual 24-hour urine collections that were conducted on the same day. And then to estimate usual intake, we estimated excretion adjusted for regression dilution bias, as often conducted in many epidemiologic studies, to correct for random error. And this is done by taking repeated measurements of urine samples over between 30 to 90 days apart in a subset of 448 people. So from the test-retest reliability, we can adjust for random error and adjust for regression dilution bias. Now, here we have the main findings from our validation study. So on the left, we have a scatter plot showing measured versus estimated sodium excretion, with estimated sodium excretion on the x-axis here, measured excretion on the y-axis. You can see that in the scatter plot, there's good correlation and agreement between the two measurements. The interclass correlation coefficient is 0.71, and the test-retest ICC value was 0.68. So there's good correlation and agreement. And similar results are found for potassium. On the right-hand side, we have sodium excretion versus systolic blood pressure, because we also need to validate the measures to see if they could detect signals with blood pressure. And we have sodium excretion, low, medium, high on the x-axis, and systolic pressure on the y-axis. The dark circles are measured 24-hour excretion. The white circle is estimated 24-hour excretion from the morning fasting urine. And you can see, first of all, with both of the measures, you see there's a positive association between sodium and blood pressure. Secondly, you also see that at each level of sodium, the level of systolic blood pressure for both of the measures is the same. So both of the measures are very robust in estimating excretion and in finding associations with blood pressure, which means that this would be a good measure to assess sodium intake in large groups of people in population studies. We would not use a morning fasting urine to assess sodium intake in a clinical setting in individuals. It would be used for large population studies. For clinics, we would certainly recommend a 24-hour urine collection, but for large studies, we can use fasting morning urine. Now, here we summarize the characteristics of participants in the PURE study. Over 100,000 people. Mean sodium excretion was 4.9 grams per day in the global sample, which is a little more than 2 teaspoons of table salt. Potassium intake was 2.1 grams per day. Most people don't get enough potassium in their diet. And the mean age is 51 years, about an equal representation of men and women. And about half of the participants were from Asia. So because people were selected from communities, this is generally a healthy cohort. So here we have sodium and potassium intake by geographic region. First, on the left-hand side, we have sodium intake. So sodium intake ranges from about 3.7 grams per day in Malaysia to about 5.5 grams per day in China. Now, in North America, the intake is about 4 to 4.2 grams per day. North America and Europe, 4.2 grams per day, which is consistent more or less with the previous literature. And also it's worth noting that China has a markedly higher intake compared to other regions of the world, about 5.5 grams per day, which is entirely consistent with the Intersalt study. And then on the right-hand side, potassium, we see North America and Europe have the highest potassium intake, whereas Malaysia, South Asia, and Africa have the lowest potassium intake. Okay, so here are the main findings from our first paper, looking at here systolic pressure versus sodium intake. So sodium is shown on the x-axis ranging from less than 2 grams per day to greater than 10 grams per day. So because of the sheer size of the study, we have over 100,000 people, and the fact that it's global, we have a very broad distribution of sodium intake. That's a major advantage of the PURE study. It has never allowed anyone previously to assess the effect of sodium across a wide range of intake with such high statistical resolution. And the y-axis is systolic pressure. The white circles are data from China. The dark circles are rest of the world. And we plotted China separately because, first of all, we had 45,000 people from China. So that's a large number of people, so we could look at China separately. And secondly, remember, China had a markedly higher level of sodium intake compared to the rest of the world. So it makes sense to look at China separately, given that they had a different sodium distribution compared to other regions. And you can see from the figure that in both China and the rest of the world, there's a positive association between sodium and blood pressure. But what's interesting is that it's a non-uniform association. So at lower levels of sodium excretion, less than 3 grams per day, there's only a 1 millimeter mercury increase in systolic pressure per gram increase in sodium. At moderate levels, a 2 millimeter mercury increase, and at high levels, 3 millimeter mercury increase. So you start to see a steeper slope as you get to higher levels of sodium intake. And the take-home message with that is that in populations that are consuming higher levels of sodium, like China, for instance, it makes sense to get them down to a moderate level. You get bigger bang for your buck when you take populations with a high sodium, bring them down to moderate levels. But in populations consuming moderate levels, getting down to low levels would have a more modest effect on blood pressure. So it's a law of diminishing returns. The more you lower your blood pressure, the less of a benefit you see. The more you lower your sodium, the less of a benefit you see as far as blood pressure reduction is concerned. And the other thing is that this also further validates the measure in 100,000 people around the world. We see a relationship as we would expect with blood pressure. And then we also looked at the effect in population subgroups. So overall, there's about a 2.1 millimeter mercury increase in systolic pressure per gram increase in sodium after correcting for random error, which is completely consistent with the randomized controlled trials. If you look at the recent Cochrane meta-analysis by He et al., showed exactly the same slope overall in the trials. And now when we look at by population subgroups, in people who consume low amounts of sodium, there's a modest increase in systolic pressure per gram increase in sodium, and it's not statistically significant. But at higher levels of sodium, you see there's a substantial increase in systolic pressure per gram increase in sodium. This is also consistent with the trial data. It shows exactly the same thing. At higher levels, you see a larger effect, a steeper slope. In people who have normal blood pressure, you see a modest increase in systolic pressure, but in people with hypertension, you see a more pronounced increase in systolic blood pressure. And by age, same thing. Younger individuals see a modest impact, but in older individuals, you see a more pronounced effect on systolic pressure, again, consistent with what we already know. So this further corroborates previous studies, and again, importantly, provides assurance as to the validity of our measurements in a large study of 100,000 people. And of course, the effect of sodium is not universally the same to everyone. Different subgroups respond differently to sodium. And so far, we've only looked at blood pressure up to this point. Now, potassium is also important. Here we have blood pressure according to sodium and potassium excretion, on the left side looking at systolic pressure. The lowest level of systolic blood pressure is found in the group that has a low level of sodium combined with high potassium. And the highest blood pressure is found in people with high sodium combined with low potassium. There was a 12 millimeter mercury difference between the groups, so it's a big difference. And a similar pattern was found for diastolic pressure. So it's not just a sodium story, it's also a potassium story. Potassium is also important. So to summarize so far, sodium intake is more strongly related to blood pressure in those with high sodium intake, in those with hypertension, and older individuals. And our findings indicate that a targeted approach to sodium reduction is more appropriate for populations with moderate intakes, like less than 5 grams per day is found in North America and Europe, whereas in populations with a higher level of intake, like found in China, then a population strategy appears to be more reasonable. It makes sense to get the population shifted down to a moderate level. Now, how feasible is population-wide sodium reduction? So far, we've only assessed generalizability, but how about feasibility? So we looked at the percentage of the global population that meets current guidelines on sodium, as presented earlier in this talk, the 2.3 gram per day target, like the upper tolerable limit, and the recommended 1.5 grams per day. So here we have two curves showing the frequency distribution of sodium excretion. The red curve is sodium excretion based on a single morning fasting urine. The blue curve is usual sodium excretion after adjusting for random error. You can see the mean level of sodium is 4.9 grams per day. Now, based on a single urine measure, only 3% of the global population met the 2.3 gram per day target. And less than 1% met the 1.5 gram per day target. And when we adjust for random error in the measurement, then we see that less than 1% met the 2.3 gram per day target, and virtually nobody consumes less than 1.5 grams per day. So the human experience for low levels of sodium intake is extremely sparse, despite the long-held position that we should get the entire population down to these levels. So in short, nobody eats what we're currently recommending. Nobody around the world, except maybe for a few hunter and gatherer societies. Malaysia? Oh, why in Malaysia? Why is Malaysia so low? 3.7 grams per day. That's pretty much on par with Western countries. I wouldn't say it's low. It's moderate. There's very little data on Malaysia for previous studies, so it's kind of hard to answer that. I would estimate that or put out there the possibility that the food supply is pretty similar to Western countries. In China, obviously, there's a large amount of discretionary salt use. So a lot of salt added at the table or while cooking. So they have very high amounts of sodium. Whereas in a lot of the Western countries and some of the upper middle income countries, the sodium is included in the food supply in processed foods or packaged foods. So this speaks to the feasibility of getting entire populations down to very low levels. So less than 5% of the population have a sodium intake below 2.3 grams per day and less than 1% below 1.5 grams per day based on a single measure. After adjusting for usual intake, almost nobody around the world consumes less than 2.3 grams per day. Now, up to this point, none of these studies address the crucial question, does lowering sodium intake reduce cardiovascular disease? Now, as you know, randomized controlled trials are the standard for assessing the efficacy and safety of an intervention. Now, up to now, the most often cited trials by far on sodium reduction and clinical events is the TOPE 1 and 2 trial, which were published in 2007 in the British Medical Journal. And it's important to note that the TOPE trial was designed to assess the effect of sodium reduction on blood pressure. It was not designed to assess long-term impact on clinical events. But what the investigators did is they looked at the extended follow-up of TOPE participants to see if the initial baseline urine measures are related to long-term health outcomes. So in short, they had no idea what these people were eating during the course of the extended follow-up. But anyway, what they found was that the low sodium group compared to the moderate sodium group, there was a trend for a beneficial effect of sodium reduction on clinical events. You could see relative risk, TOP1 0.72, TOP2 0.88. But none of the effects were statistically significant. There was a pretty modest number of events in these studies. A major drawback was the fact that 23% of individuals were lost to follow-up during the course of the follow-up, and a further 1/3 had missing information on cardiovascular events. So in short, about 40% of the outcome data was missing. That's a major threat to the internal validity of the study. And again, this was during the extended follow-up. We don't know what people were eating during that time. So in the absence of good randomized controlled trial data, we turn to the observational data to look at sodium's effect on long-term clinical outcomes. So in 2010, Struzzulo published a meta-analysis of prospective cohort studies in the British Medical Journal, and he looked at the effect of sodium on cardiovascular disease, MI, and stroke. But what he did was he compared the lowest quintile to the highest quintile. So he compared quintile extremes, which carries the assumption that the relationship between sodium and clinical events is linear. But as subsequent studies showed, that assumption is completely false. But nevertheless, they found a 17% increased risk of cardiovascular events in the highest quintile compared to the lowest quintile group. So a year later, we repeated the meta-analysis by Struzzulo, but we stratified by geographic region. So we took the Asian countries, we looked at them separately, and we looked at Europe separately and North America separately. The rationale for that is that we know that Asian countries, particularly these studies mostly East Asian countries, had a markedly higher level of sodium compared to Western countries. And remember the blood pressure curve we put up earlier, you see a much stronger relationship with blood pressure at higher levels of sodium. So it makes sense to look at Asia separately. And what we found is that in Asia, when we look at the papers conducted in Asian populations, where average intake was 4.3 to 5.7 grams per day, you see that there's a 68% increased risk of stroke in the highest quintile compared to the lowest quintile of sodium. In the United States and Europe, which had a moderate level of sodium intake, you could see that there's no relationship, no significant relationship. So the level of sodium intake in the population largely is an important determinant of whether you find a relationship with clinical events. Now, since the Struzzulo paper, there's been recent developments. There's been 6 new prospective cohort studies that have been published since 2009, and all of them have used urine collections. And it's very important to use urine collections for the purpose of assessing sodium intake in populations. Dietary assessment is not an accurate way to assess sodium in populations because it's not very good in capturing discretionary salt use, for instance. So in light of this new evidence, the Institute of Medicine, IOM, expert panel was convened in 2012 to study the evidence. Now, among these new studies that the IOM considered in 2012, and their final report in 2013. The largest by far was conducted by our group here at McMaster, the data from the on-target study. So in the on-target participants, over 28,000 people, we looked at the relationship between sodium and clinical events in a high-risk population. These are people that have had a previous myocardial infarction, have cardiovascular disease or heart failure, or type 2 diabetes. So these are high-risk population, and they're also older individuals above the age of 60. And they were followed up over a 56-month period, and sodium was assessed in the same way that I described earlier, using the fasting morning urine method. And the principal outcome was a composite of cardiovascular events, which included mortality, stroke, MI, and heart failure. And after the follow-up, there were over 4,700 events. And you could see in the figure, sodium on the x-axis shown here and the hazard ratio on the y-axis. The spline curve shows that there's a U-shaped or J-shaped relationship between sodium and clinical events. So when intake exceeded 6 or 7 grams per day, you start to see a steady rise in the risk for cardiovascular events or mortality. But also at low levels of sodium, less than 3 grams per day, you also see an increased risk. So being in the middle was optimal, having between 3 to 6 grams per day, which is also where most of the population lies. About 3/4 of the global population is here, which is actually the lowest risk group. Oh, yeah. Yeah. Yes. Yes, a great point. So for the purpose of confounding, this was a study that collected a lot of detailed information because it was a clinical trial. So there was a lot of detailed information collected on potential confounders like lifestyle, diet, alcohol. So we control diet, fruits and vegetables, alcohol intake, physical activity, smoking, comorbidities. And of course, education, age, sex, the typical standard potential confounding variables. And we did various model building from univariate to multivariable models. The findings were quite robust. For the interest of time, I'll focus mostly on pure, but we did extensive analyses in the results. No matter how we looked at it over a 1-year period, the results wouldn't go away. We saw the same shape, the same relationship, no matter how you looked at the data. So again, being in the middle was optimal. Now, as Robbie mentioned, there's the potential for reverse causation because you could have in a high-risk population, perhaps it's the people that are the sickest who are consuming the lowest amount of sodium. They're reducing their sodium intake because they're sick or they're more sick. So there is the potential for reverse causation in this on-target study in particular. And even though we excluded people with an event in the first couple of years and the results remain the same, still there's always the potential of reverse causation. The majority of participants had RAS blockers, and at that time it was a limitation that the method of estimating sodium intake, which was not extensively validated, but since then we did validate it as I presented already. So, but the reverse causation issue is important. So anyway, so the IOM report in 2013 considered the results from OnTarget, which I just showed, and 4 other papers. And their conclusions were that new studies support current efforts to reduce excessive sodium intake in order to lower the risk of heart disease and stroke. The evidence on health outcomes does not support reduction of sodium to less than 2,300 milligrams per day, which is completely the opposite from what the previous IOM report said before that. It recommended optimal would be 1.5 grams per day. So they went away from that. So now they're saying that it doesn't support less than 2,300 milligrams. They did not specify an optimal range. They said they don't know what the optimal range. More research is needed. And there's no evidence on health outcomes to support treating population subgroups differently from the general U.S. population. They said more research is needed to understand population subgroups. And further research is needed to shed light on the association between at lower levels of sodium, between 1.5 to 2.3 grams per day, to better understand the nature of the relationship at lower levels of sodium. So that brings us up to the present with the second paper that we published in the New England Journal, in a paper led by Martin O'Donnell, myself, and Dr. Salim Youssef here at McMaster and PHRI. We looked at urinary sodium and potassium excretion, mortality, and cardiovascular events. So again, the same participants, the PURE study, over 100,000 people, about 8% had a previous history of cardiovascular disease. The mean exposure I've already described, sodium and how we measured sodium. And the primary outcome was a composite of cardiovascular death, non-CVD death, stroke, MI, and congestive heart failure. There were a total of 3,317 events after a 3.7-year follow-up, and 95% of the follow-up was complete. There's available data on 95% of participants. Multivariable logistic regression with GEE models were conducted, and analytic approaches to address confounding and reverse causality. And I'll show you how we did that. So first, we have here a spline showing the main results, showing sodium excretion versus risk of death or clinical events, the primary composite outcome. You could see that there is a U-shaped or hockey stick relationship between sodium and the primary composite outcome. So at higher levels of sodium, above 6 or 7 grams per day, you start to see a bit of an increase in the risk for cardiovascular events or mortality. And also at lower levels, less than 3, particularly less than 2 grams, you start to see also an increase in risk for the primary outcome. So again, the optimal level was about between 3 to 6 grams per day, consistent with the other data from OnTarget. So again, unlike OnTarget, was a generally healthy population, global population of people selected from communities around the world. Similar results were found for all-cause mortality. Again, you see the same shape relationship. Similar results were found for risk of a major cardiovascular event. Now, looking at the univariate and multivariable models, in univariable model, adjusting for just age and sex, you see that at higher levels of sodium, there's about an 18% increased risk for the primary composite outcome. And at lower levels of sodium, less than 3 grams per day, there's about a 24% increased risk compared to the moderate level, about 4 to 6 grams per day. And after multivariable adjustment, we collected detailed information on potential confounders, education, prior cardiovascular history, comorbidities, alcohol intake, lifestyle, exercise, alcohol intake, dietary assessments, diabetes, body mass index, current smoking, almost everything that you can imagine. We adjusted for everything. And sorry, yes, we also adjusted for total energy in one of the subsequent models. So we did increased model building, and I'll put that up in a second. We did that, yeah. And
you probably mentioned it already. Why you chose a 2-gram interval for certain species in the middle.
Yeah.
There, looking at the graph.
Yeah.
Good as the best one, 4 to 5.
Yeah. 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 The main reason. Yes, sir. Yeah. Yes, I'm sorry, I keep forgetting, yes. Oh, yes, very good question, Holger. So the question is, why did we pool together the reference group being 4 to 6 grams rather than using a more finite group, 4 to 5 or 5 to 6 being the reference group? And why did we pool the reference group? And the main reason for that was that the effect was very similar in the two groups and it's increased statistical power. That was the main reason. And the other thing is that's also where the median level was in the general population, where the main part of the distribution, the peak of the distribution lies. That was mostly statistical. Yeah. Yes, and so despite adding all the different potential confounders to the model, you can see that the estimates are very robust. There's a 27% increased risk of an event in the people in the lowest group compared to moderate, and 18% in the highest group. So the results are unaltered with multivariable adjustment, which gives us more confidence as to the accuracy of the results and the potential for unmeasured confounding and influencing the results. Hold it. Yes, yes. That's the adjusted multivariable model. Yeah.
Because I'm responding, so if you recall, why you take that reference interval, looking at the spline, it looks to me like the effect starts to increase at around 5 grams, right?
Yeah.
The alteration starts to increase at around 5 grams. Because people expect power, and that's why I'm interested in the power. The power will increase with larger effect sizes as well, right?
Right.
So there's a trade-off between using the larger population size and the larger effect.
Right.
How you make that decision?
Yeah, it didn't really make any. It didn't have any impact on the final conclusion of the study, and I recall from discussions we had with Martin at that time when we were doing the analysis, we just decided that to increase power, to have a bigger reference group to pool them, but it didn't make any difference in the final conclusion. Certainly, it didn't make any difference in the high end, what the effect would be, and also in the low end. But you're right, the spline does provide more information as to the shape of the relationship more precisely than the other analysis. The two complement each other. Yeah. So, yeah. And then okay. So here, I apologize if you can't read the print. So this is one of the tables from the paper. So compared to the reference group, 4 to 6 grams per day, we have the other groups that we're looking at here. So this is the primary model, which I presented in the previous slide. Now, we did increasingly adjusting for other potential confounders to examine the potential for confounding. So we added LDL, HDL cholesterol to the model, which was in 80% of the participants in the study that we had information on. And you can see that the estimates are pretty much the same with that adjustment. We also added dietary factors into the model. Russ was asking the question earlier. So when you add dietary factors, including fruits and vegetables and energy intake, you see that the estimates are, again, unaltered. You see significant effects at both ends. Now, we also added blood pressure to the model. Now, blood pressure is not a confounder, but it's a mediator, a variable along the causal pathway from sodium to long-term health outcomes. So, so we would expect that when you add blood pressure to the model, it would attenuate the effect of sodium on health outcomes at the higher end. And indeed, you see that when you add blood pressure to the model, the estimate at the high end, greater than 7 grams per day, is significantly attenuated. So now you get a non-significant effect on cardiovascular events. So blood pressure largely determines the extent of sodium's effect on health outcomes. But at the lower end, look at this. When you adjust for blood pressure, the effect of low sodium on cardiovascular events remains, even with the adjustment for blood pressure. So that means that the effect of sodium on health outcomes is independent of blood pressure. There's some other pathophysiologic mechanism taking place to explain that. Then in sensitivity analysis, we excluded people with baseline cardiovascular disease and baseline cancer, to reduce the likelihood of reverse causation, get rid of the people that had illness at baseline. And when you do that, you can see that, again, the estimates are the same. Then we looked at a very low-risk cohort. So we did a propensity score matching, and we identified people that would be at very low risk for cardiovascular disease, about 60,000 people. And in that cohort, again, you see the results are the same. In fact, if anything, they're more pronounced at the effect for low sodium. And then to further reduce the likelihood of reverse causation, to explore that, we excluded people that had an event in the first year and excluded the people that had an event in the first couple of years. And when you do that, again, you see that the results are the same. And by excluding people that had an event in the first couple of years, you would identify those people that perhaps were missed during the baseline screening that may have had asymptomatic disease. So again, it addresses the issue of reverse causation. And you can see the results are the same. So we analyze the data every humanly way possible, and the results are the same. So we think that this effect at the low end is real. And we should really be very careful before recommending entire populations consume very low levels of sodium. We also looked at subgroups, hypertension individuals and people without hypertension. In people with hypertension, you can see again, compared to the middle reference group, having high level of sodium and low level of sodium was associated with increased risk. And people without hypertension, you can see that low sodium was associated with increased risk, but high sodium was not associated with risk. So in people with hypertension, we would try to get them down to a moderate level between 3 to 6 grams, perhaps at the lower end of that moderate level. Whereas in non-hypertensives, it's just important to keep them out of the low sodium group. So ours is not the first study to show that low sodium is harmful. Our findings are consistent with the data from 4 or 5 other recent studies that have been published using urinary measures. So here's one, Ikenichi Diabetes Care. They looked at patients with type 2 diabetes and found that low sodium was associated with more all-cause mortality. And Thomas, in Diabetes Care 2011, showed that both high and low sodium were associated with all-cause mortality in patients with type 1 diabetes. And again, being in the middle was optimal, where most people lie. So another study that shows a J shape. In another paper published in JAMA 2011, this is in 3,681 people who were healthy at baseline. Again, low sodium was associated with increased risk for cardiovascular events compared to higher sodium. And the lower the sodium, the higher the risk. And most recently, a new paper showed that 3.5 grams per day was optimal, with we here in Western countries mostly, but having a higher intake and a lower intake was associated with incident heart failure in data from the Norfolk EPIC study of generally healthy people. So study after study has been showing the same signal. Now, why might low sodium intake increase the risk of cardiovascular disease? What's the mechanism to explain the potentially harmful effects of low sodium? Well, a paper published by Bruner in 1972 in the New England Journal of Medicine showed quite well the inverse logarithmic relationship between sodium and plasma renin activity and aldosterone. So that when you reduce sodium intake to very low levels, you start to see an exponential rise in renin and a rise in aldosterone. And we know that these are damaging to the vasculature. So that's one possible mechanism to explain that. Up to now, though, there's been no study that has directly made the link in the same participants. So, for instance, this study by Bruner did not have clinical events assessed, long-term clinical events, to directly make the link in the same participants. So that's something that we can explore. I'll tell you about that in a moment. So the HOPE trial showed, for instance, that increased plasma renin activity is associated with cardiovascular disease mortality. So again, further providing a possibility that renin and angiotensin and aldosterone are the possible mechanism. Grotto, in a new meta-analysis, also showed that there's a J-shaped relationship between cardiovascular disease and sodium. So they looked at in their systematic review, the different cohort studies that have been published to date. Several showed that moderate sodium was more beneficial than low sodium. Several studies showed no effect, and a few showed that low sodium was more beneficial, but those studies had a small number of clinical events. The results were not as clear-cut. Generally, Grotto's paper concluded that the reference range is between 2.7 grams per day to 5 grams per day. That was their conclusion, which falls almost spot on with the pure study. Okay, for potassium, we found that it's protective. More potassium you eat, the lower the cardiovascular disease risk in the same participants in pure. And the same thing was found for total mortality and for major cardiovascular events. And then we did multivariable models versus univariate. The results were robust, even with increased adjustment for potential confounders. And we also did different multivariable analyses, like we did with sodium, we did with potassium, and found the results were very robust, no matter how you analyze the data and what potential confounders you throw into the model. Or what? Yeah. Yes. Yes. Fruits and vegetables. Okay. Sorry. Yeah. Sorry. It's easy to forget. Sorry. The question is urinary potassium, is that the same thing as increasing fruits and vegetables? And to a large extent, yes. And mainly, I would say yes. But although low-fat dairy products and whole grains also contain a fair amount of potassium as well. They're good sources of potassium. If you follow an all-around healthy diet, then you probably have high levels of potassium. Yeah. Yes, yes. Yes. Yeah, because and the main reason is because it doesn't matter. The question is why is the reference group different for potassium versus sodium? The answer is it doesn't really matter. You're still getting a linear relationship. Linear. The other one is also because with sodium it was a J-shaped or U-shaped relationship, so it makes sense to have the middle as the reference group. Whereas if you use the ends, you won't quite see the effects quite as well. So that's also the other reason. And so no matter which group you use, you still see the effect. And yeah, so anytime. Yeah, so that's that. So to summarize, I don't know what time it is exactly. Okay, so we have a little bit of another couple minutes. So to summarize, the vast majority of the global population consumes greater than 2 grams per day, despite different diets around the world and different sources of sodium. So most of the global population consumes between 3 to 6 grams per day, about 3/4 of the global population. Most people are in that moderate range. And there's a significant association between sodium intake and blood pressure that's most evident at higher intake ranges. Excess cardiovascular risk is found in people with a sodium intake greater than 6 grams per day, which is mostly observed in those with hypertension. Low sodium intake was not associated with lower risk than moderate intake despite lower blood pressure. In fact, it was associated with higher risk. And higher potassium was related to lower cardiovascular disease. So our findings support reducing sodium intake to moderate levels, from high levels to moderate. Moderate sodium intake between 3 to 6 grams appears to be optimal for those with hypertension, and we could target the lower end of that range for people with hypertension. And this casts considerable uncertainty about whether low sodium intake results in net clinical benefit and calls for definitive randomized controlled trials. So because largely the topic is largely political, so it will be debate without end without a randomized controlled trial. Otherwise, there's people that believe the blood pressure data is more important, and then there's a relationship with blood pressure. That's all that counts. But there's others that believe no, it's the health outcomes that are more important. So and you get this fierce debate. So unless a randomized controlled trial is conducted with long-term health outcomes, I think it will be just the debate without end. And so the important message for the public is to adopt a healthy dietary pattern rich in foods containing potassium, fruits and vegetables, with moderate amounts of sodium. Increase physical activity and don't smoke. I mean, that's the bottom line. So Susan Opperl, who was the head of the American Heart Association, wrote a beautiful, I think beautiful, commentary about our 2 New England Journal papers. She said, these provocative findings beg for a randomized control outcome trial to compare reduced sodium intake with usual diet. In the absence of such a trial, the results argue against reduction of dietary sodium as an isolated public health recommendation. This is Susan Opperl. And the IOM report last year, or 2 years ago, in 2013, called for more cohort studies or randomized controlled trials. So essentially, the IOM report walked away from surrogate measures like blood pressure, and it called for larger studies with clinical events and long-term health outcomes. And so they called for cohort studies with large numbers of people to characterize the nature of the relationship between sodium and cardiovascular events, particularly at the lower end of sodium and in population subgroups. And they also called for randomized controlled trials with clinical outcomes as the endpoint. Such a trial could be feasible in individuals living in closed communities like nursing homes or mental institutions, as has been done in some dietary studies. Because you see, long-term adherence to a low-sodium diet is a challenge. So it'd be very difficult to get people to eat a very low-sodium diet for many years to assess the effects of low sodium on clinical events. So that's why studying maybe closed communities in perhaps a cluster randomized trial, or it could be a trial of individuals but at high risk for cardiovascular disease, like people, for instance, with chronic kidney disease, so who are recommended to consume a low amount of sodium despite an absence of evidence. Perhaps that might be the way to go about studying the question. Until a trial is done, it's going to be a fierce debate up until then. And so we know that well-meaning interventions based on insufficient science can mislead, from hormone replacement therapy, margarines, and total fat intake, lessons from the past, and yet we're making recommendations despite having the evidence for people to follow that. And for future work, we'll have several things lined up. First, we could look at the extended follow-up in CURE. We're planning a 10-year follow-up where we'll have at least 10,000 cardiovascular events. We'll look at sodium and potassium versus cardiovascular outcomes and other vascular-related conditions like atrial fibrillation, renal function, and cognitive impairment. Cancers, there's some data implicating sodium with stomach cancer. Again, it's very weak information. We can look at that as well. We are collecting information on incident cancer and total mortality. We also, again, as I mentioned, as we get more events, we can look at the effects of low sodium on cardiovascular events, because since very few people consume low sodium, you need a large number of people and a large number of events to better understand that relationship. And we can look at individual events like MI, stroke, and heart failure as we get more events. And importantly, we could study the mechanism that mediates the increased risk with low sodium. Is it renin? I'll be putting in a grant looking at renin levels in these participants in a nested case control study. So at the 6-year follow-up, 6,000 CVD incident cases versus 6,000 controls, and assess whether renin mediates the relationship. And that could help us directly make the link. Interstroke, we have data on 27,000 people, case control study, 13,000 people with incident stroke. And so we could study stroke subtypes, intracerebral hemorrhage, subarachnoid, and ischemic strokes and different types of ischemic strokes. Nothing like this has ever been conducted. Nobody's ever looked at different stroke subtypes. And then lastly, we can do a randomized controlled trial. This would be eventually our goal, to study the sustained long-term effect of low sodium versus moderate intake on renal outcomes. In my way of thinking, the initial plan would be, I mentioned the cluster randomized trial, but I would think at first maybe a smaller trial of perhaps participants with normotensive individuals with chronic kidney disease, selected from renal clinics, that we can recruit and follow up for a 2-year period, and compare moderate sodium to low sodium over a modest period, like 1.5 to 2 years. That might be a start to do a randomized controlled trial. And assess, for one thing, the feasibility of a 2-year low sodium diet. And I think I'll stop there. Just one slide. So the IOM committee chair in 2003, Brian Strom, stated, "It's not a question of studies showing benefit being better than those showing harm, sodium lowering versus moderate levels. There is no data showing benefit with sodium lowering." Right? Thanks very much. And we have plenty of time for questions, I think. Okay, way at the back first. Dr. Hinks? Oh, you are? Yeah. Yeah. Okay. These are all great questions. Okay. I'll take them one at a time. I'll try to repeat them. So one is you're saying that the message should not be to reduce intake in the entire population, to not use a population-wide approach, rather than instead focus on reducing sodium in individuals with high intake. Is that what? Yeah, because okay, but here's the thing with that. Okay, so the point Dr. Haynes is making is that you know, we have to be careful before making recommendations based on observational data, given perhaps lessons from the past, like with hormone replacement therapy. But first, that point about hormone replacement therapy, the good observational studies, if you go back and look at that, the good observational studies did show that hormone replacement therapy is potentially harmful. Just generally across the board, if you look at, despite methodologic quality, if you look at all the studies, that wasn't the case. But if you look at the good, well-conducted studies, they did show that hormone replacement therapy was harmful. A lot of people don't kind of skip over that point, and that's true. I mean, we've looked at this ourselves as a group. But anyway, but what the people who are calling for us to be cautious with the observational studies, they're making recommendations based on short-term surrogate measures, without relying on blind faith that the effects will be extrapolated to cardiovascular events. And unless they demonstrate that clearly that would be beneficial, given these data of potential harm, I think we really need to be careful before recommending the entire population to get their intake down to low levels, even if it was feasible. And that's the other issue. You mentioned feasibility. It's not even feasible anyway, right? And yet it's these same people that are recommending that we consume low amounts of sodium. They're saying that we can't do clinical trials. This is what they're saying, that we can't do clinical trials because it's not feasible to get people on a low sodium diet. But then why are you recommending that diet to everyone? If you're recommending that diet, then it seems kind of strange that people are saying that we can't do randomized controlled trials. So it seems like a bit of a mixed message there. But, I think. Oh, sorry, Dr. Truman? Okay. An online question? Okay.
You want to make it first?
Okay, good, very good question. So in our analysis, we did I didn't show here in the interest of time, but we did sub-analyses or sensitivity analysis where we excluded the people that were taking blood pressure medication, and the results were the same. That's what you can do. You just exclude them and see if the results are the same in those when you exclude them and the results were the same. Yeah. Dr. Schumann?
There's almost everything that's blind set except for that I'm not certain how you wouldn't give advice to the possibility, because the question is really not going to go away. And that makes me a little uncomfortable. I would also not make any recommendations and not just position there. Also because I think this is one area where conducting a low risk of bias trial is not going to be feasible. Because controlling for the co-interventions that the unwanted co-interventions that you have when you reduce sodium intake, controlling for those in analyses or in the trial design, it's practically infeasible.
Yeah.
You're going to have weight changes. You give people a different diet system. How are you going to extract sodium? And how are you going to provide similar diets that are similar to caloric intake with other potential risk factors for cardiovascular events?
Yeah, exactly.
How are you going to do that, right?
Yeah.
So I would say in this area, you will never have low risk of bias on trials.
Yeah.
And all that you might have is what you're producing, what you produce here.
Yes.
So
yes.
First point.
Great point.
That you've already mentioned it, and I think again, how did you account for these issues? Because the raw sodium output or intake will call it dietary intake as rather than which leads to weight changes, etc., or different
Yeah, these are all great points. I'll take the second point first. So the question for the audience that's not here, question is how do we account for other issues like the diet that could vary or different body mass index or other measures higher caloric intake. Yeah, exactly. So we had dietary assessment in our participants, about 85% of participants. So in one of the multivariable models that I put up here, I'll bring that up now. This is the potassium. Yeah. So in this model here, and other models as well that we conducted, where it was that the dietary factors we added to the model. We added fruits and vegetables and energy intake, and when adding that to the model, you can see that the effect both at the low end and the high end still remains unaltered. So no matter how we analyzed it and what we added to the model, the results were the same. It's the only thing really you can do in an observational study, and we applied it. Certainly, again, it does not 100% guarantee that there's no reverse causation, but given with the increasing level of adjustment and the different sensitivity analysis that we conducted in a very rigorous manner, it seems unlikely that that would be the explanation at the low end here to see the increased risk. The other criticism that comes up is that we took a single urinary measurement. This is that often comes, to assess sodium intake, you have to do multiple 24-hour urine collection. First of all, that's just not feasible. It's not going to happen. No one's ever going to do that, right? So there's no point just dwelling on that. But if it's a methodological limitation, as they keep bringing up, when you think about that, if you take a single urine measurement, that would introduce random measurement error. Because, some people have a higher intake one day and a lower intake another day. In the long term, in large numbers, that would average out. So that's random error. So that's not going to take a linear relationship and turn it into a U-shape. So this is another criticism that comes up and doesn't really address the findings carefully. But any other? Oh, yeah. Yes. Yeah, no, I completely agree with you, Dr. Schuneman. So the other point Dr. Schuneman raised was the other issue was that that it would be very difficult to do a randomized controlled trial because despite the sodium intervention, you're going to get other changes of the diet, like different aspects of the diet will be different in the groups. So it'd be very hard to isolate the effect of sodium because other aspects of the diet are changing as well. So wait a second. Okay. Yeah. So yeah. Sorry. I'm sorry. So just to address Dr. Schuneman's point, that I agree that other aspects of the diet will be changing as well. So it really turns into an observational study. Yeah. Yeah. Any more? Any more questions? It's 5 anyway. Yeah. I'll be happy to take questions individually. Oh, yeah.
Thanks, Andrew. I suggest that people who still have questions talk to Andrew now after the talk. It's 5 already. Thanks very much, Andrew, for the presentation. And I invite everybody to come next month to see Dr. Alan Amster for Rounds.